Now we get to the topic that's going to be very important to us when we're solving systems of linear differential equations. We want to talk about eigenvalues and eigenvectors. So here's the important definition. We say that the number lambda is an eigenvalue for an n by n matrix A if there's a non-zero vector x with ax equal lambda x. We'll use the vector notation like that. We then say that any such vector x is an eigenvector for A corresponding to that eigenvalue lambda. And we would like to know, how can we tell when a vector is an eigenvector? And we're going to be talking a lot about this later. What does it mean to be an eigenvector? Let's talk a little bit about that first. If you think of x, which is this vector x1 through xn, this is a vector in Rn, in n-dimensional real space. When we apply A to it, we get another vector, which is, again, in Rn. You can think of A as an operator. It will be a linear operator from the space Rn to itself. And you can think of it as transforming the vector x into the vector Ax. What's special about eigenvectors? Well, if x is an eigenvector, then Ax is just a scalar times x. X is transformed through this multiplication on the left by A, the matrix A, into a vector that's in the same direction. When we have lambda times x, that's in general a vector parallel to x. It's either the same direction, or if lambda is negative, it's in the opposite direction, which we'll still refer to as the same direction as the vector x. Geometrically, that's a very important property, and we're going to see how, when it comes to algebra with matrices, there are all sorts of really great special things that happen when you have eigenvectors and eigenvalues. So let's go back to the question, how can we tell if x is an eigenvector? Well, I'm going to take this equation and write it a little bit differently. That's the same as writing ax minus lambda x equals 0. And another way of writing that is a minus lambda times the identity multiplied by x is equal 0. And here we have the 0 vector. The 0 vector is just a vector with all zeros as its entry. Why do I have a minus lambda I times x? Well, a times x is just ax. And then lambda I times x is just lambda times x. The identity times x is just that vector x itself. So what does it mean for x to be an eigenvector? X is an eigenvector if it's a non-zero vector. X is an eigenvector, I should say, with eigenvalue lambda, if x is a non-zero vector that makes this true. Well, when will this equation have a non-zero vector x that makes it true? Well, the answer is that will happen precisely when this matrix is singular. Why singular? Because if it were non-singular, if it had determinant which is not 0, there would be a unique solution to this vector equation, which is equivalent to a system of n equations in n unknowns. And if there's a unique solution, you already know what it is, because if x is the 0 vector, that is a solution. So if we think of this as an equation with the vector x as an unknown vector, the 0 vector works. The question is, do other vectors work as well? And the answer will be yes, exactly when this is a singular matrix, and that will mean its determinant has to be 0. So this will have solutions with a non-zero vector x precisely when lambda is an eigenvalue. So I can write lambda is an eigenvalue exactly when a minus lambda I is singular which is the same as saying, let me write that here, that the determinant of a minus lambda I is exactly 0. Now, if we look at that thing, which is a very important quantity, the determinant of a minus lambda I, we'll call that the characteristic polynomial for an n by n matrix. We'll see an example of this in a minute. This will always be a polynomial in the variable lambda of degree n. So the characteristic polynomial of an n by n matrix is just an nth degree polynomial in lambda, and lambda will be an eigenvalue for A precisely when this determinant is 0, which means exactly that lambda is a root of the characteristic polynomial. That number lambda makes this determinant equal to 0. Let's see an example here. Can we find what are the eigenvalues of this matrix A? And then we could ask the question, what are the corresponding eigenvectors? Well, let's start with the eigenvalues. To find the eigenvalues, we want to look at the characteristic polynomial. The characteristic polynomial is this determinant of A minus lambda I. Of course, here, lambda, the identity is just this matrix, 1, 0, 0, 0, 1, 0, 0, 0, 1. So lambda I is that times lambda, which is just what you get when you have lambdas down the diagonal. And A minus lambda I is the matrix 2 minus lambda minus 1, 0, 0, 1 minus lambda, 0, and 0, 1, 2 minus lambda. And we can compute that determinant in the way that we've already learned here. We take the first element, 2 minus lambda, and we multiply by the determinant of its minor matrix, which is 1 minus lambda times 2 minus lambda minus 0. And then we subtract -1 times the determinant of its minor matrix, but there'll be 0 and 0 here, so you'll see that the determinant of the minor matrix here is exactly 0. And then we add 0 times the determinant of its minor matrix, which will be 0. So in the end, we get the characteristic polynomial very quickly. It's just 1 minus lambda times 2 minus lambda squared. And there's no reason to expand this out, because what I'm really interested in are the roots of this characteristic polynomial. So the roots are lambda equals 1 and lambda equals 2. And it will be useful to note that this root, lambda equals 2, has multiplicity 2. And even though we won't go into all the details, let me tell you what knowing the roots and their multiplicities tells you about the eigenvalues. When you have an eigenvalue that's a root of just multiplicity 1 from the characteristic polynomial, that tells you that there will be one unique eigenvector. And when I say unique, it won't exactly be unique. Any non-zero multiple of it will be also an eigenvector. So really what we mean is that the eigenspace, the space of all eigenvectors with eigenvalue 1, and then you throw in the 0 vector as well, that space has dimension 1. In other words, it's spanned by a single non-zero vector. So when we talk about there's a single eigenvector corresponding to lambda equals 1, we means one vector which is a basis for the entire eigenspace corresponding to lambda equals 1. That means all eigenvectors with that same eigenvalue would just be multiples of that one vector that you find. Things can be a little more tricky when you have an eigenvalue of multiplicity 2 or greater. When you have an eigenvalue with multiplicity 2, you might have just a one-dimensional eigenspace, just a single one vector, non-zero vector, which is a basis for the set of all eigenvectors of eigenvalue 2. But you might have a two-dimensional eigenspace, in which case there would be two independent eigenvectors with eigenvalue 2. But because the multiplicity is 2, the maximum dimension of the eigenspace is 2. So you'll have either one independent eigenvector or two independent eigenvectors. If you had a much larger matrix and a much higher degree characteristic polynomial, you might have eigenvalues with multiplicity 3, 4, 5, or whatever. If you have an eigenvalue, for example, of multiplicity 5, you can have an eigenspace of dimension anywhere from 1 through 5. In other words, you might have one independent eigenvector corresponding to that eigenvalue, or 2 or 3 or 4 or 5 independent eigenvectors corresponding to that same eigenvalue. You'll always have at least one eigenvector when you have an eigenvalue, because that is, by definition, what it means to be an eigenvalue. It means you have to have a non-zero vector x with ax equals lambda x. In other words, there has to be a corresponding eigenvector. How would we find the eigenvectors? We'll do more computations later, so I'm only going to give you a very quick demonstration for one of them, the one for lambda equals 1. But I'm sure you've seen this before, so I'll let you work on eigenvectors for eigenvalue 2. How do we find the eigenvector? In this case, it's going to be just one basis vector for the eigenspace corresponding to lambda equals 1. We want to solve ax equals lambda, which is 1 times x. In other words, a minus 1 times the identity times x equals the 0 vector. Well, how would we solve that equation? We could create the augmented matrix, where you put a minus the identity here on the left. A minus the identity is the vector 1, minus 1, 0. Remember, we're going to subtract 1s down the diagonal. 0, 0, 0, 0, 1, 1. And it's an augmented matrix. We're going to put zeros on the right. And now we're going to reduce that. I would say reduce it. We're going to reduce that until what's called reduced echelon form. And we're almost there. We can start with a pivot in the upper left. That's a non-zero number. We have zeros below it already. We would like to move here to the second position in the second row for the next pivot, but that's a 0, so we're going to switch with the third row. So I'm going to do a row operation, which is just a row interchange. And put the row zeros at the bottom. And now to get reduced echelon form, I'd like to zero out everything above what are our pivot terms. So I take the first row and add to it the second row. And then we interpret these in the following way. Remember, the vector x is x1, x2, x3, like that. This will be our column for x1. This will be our column for x2. This will be our column for x3. And this will be our constants here. The first row corresponds to the equation x1 plus x3 equals 0, where x1 is minus x3. The second equation corresponds to x2 equals minus x3, because x2 plus x3 equals 0. So the vector x, which is the vector x1, x2, x3, can be written like minus x3, that's x1, minus x3, that's x2, and x3, which is just, if I factor out x3 times the vector minus 1, 1. So what is the claim? The claim is that any multiple, x3 can be any number, any multiple of x3, any multiple x3 times this vector will be a solution to this equation. In particular, as long as x3 is not 0, you'll have an eigenvector here. So if we just take x3 equals 1, we can have our eigenvector, which is going to be the vector minus 1, 1. And we should always check that this in fact works. And so how do we check that that's an eigenvector? What is the matrix A times the vector minus 1, 1. That's 2, minus 1, 0, 0, 1, 0, 0, 0, 1, times negative 1, 1. That's negative 2. This is just 2 times negative 1, which is negative 2, plus negative 1 times negative 1, which is 1, plus 0, so we get negative 1. 0 times negative 1 plus 1 times negative 1 plus 0 times 1 is negative 1. And 0, 0, 1 times negative 1, 1. When you look for the third entry, you clearly just get 1. This is just 1 times this vector, negative 1, negative 1, 1. That tells us that this vector, negative 1, negative 1, 1, really is an eigenvector corresponding to eigenvalue 1. As I said, you should take a look and find the eigenvectors for lambda equals 2. I'll leave that to you guys as an exercise.